So where did we start? Stop. So this one we're gonna have one like this for the final. So it's a static equilibrium. Make sure you know how to do it. And then this one, so when something is in equilibrium, you're gonna use the sum of all the forces equals 0 and the sum of all the torques equals 0. I cannot find the slide. So let's do a simple one. So this is a simple static equilibrium example where we can use the sum of torques equals 0 and the sum of forces equals 0. Okay, so you see they did the free body diagram for you. So you have the weight here of the swimmer, you have the normal force from the fulcrum here, they call that the fulcrum, and the bolt. Okay, it's going to pull down. And the question is, you need to find F1 and F2. So you can, if you use just the forces, so you're going to say everything up equals everything down. So then you have one equation with two unknown. So that's not going to work. So we're going to start by using the torques, right? So if you want to do it, so this is given, this is 530 Newton. And then you have to decide where to put your axis of rotation. And if in an equilibrium case, it doesn't matter. You can place it where it's most convenient to place it. So for example, if you want to eliminate force F1, so then you say, okay, my axis of rotation is going to be here. But you can place it here and you can place it there. Doesn't matter. When you place it here, you see that the torque applied by F1 relative to the axis of rotation is going to be 0 because it's not being efficient. You are just pushing on the axis, so it's not going to rotate. Now this one is going to make it go clockwise, and this one is going to make it go counterclockwise, and it's not moving. Okay, so it means it's an equilibrium. If you do it with your hand, remember a torque is a vector, counterclockwise is towards you, clockwise is in the board. So you have toward you in the board, the two torques will balance each other out. So this one is in the board, right? No, this one is towards you, and this one is in the board. But it doesn't really matter, right? It's just to review. Okay, so the torque applied by the weight relative to the axis of rotation, okay, it's going to be, I'm not going to do it this way. I'm going to do, it's an equilibrium. So the sum of the torque clockwise, it's going to be equals to the sum of the torque counterclockwise because it's an equilibrium. If you were asked just to find the torque, then this one will be negative and this one will be positive. But I'm going to do it this way. So in that case, we are only using the magnitude. Okay? So clockwise, that will be this one. So that will be 530 times the distance between where the force is applied and the axis of rotation. So 3.90 equals, so this one is going to be F2 times 1.40, yes. So in magnitude, okay, we are only finding in magnitude. Okay, that's easy. So if you do it this way, you're gonna do the magnitude. Now the book will do it this way. The sum of the torque here equals 0. So that's a vector, right? So it can be positive or negative. I do it this way, like I do up equals down. You don't have to do it this way. That's why you have to open your book to see how it's done. And there is an echo. Hello, good morning. Agree? Right? So the answer is 1466 Newton. Did you all get that? Yes? You didn't erase your memory, right, Cece? So that will be for F2. Now let's say we want to find F1. So you have two ways to do it. You can say now everything up equals everything down. Okay, because to have an equilibrium, you need to have the sum of the torques equals 0, but also the sum of the forces equals 0. So you have two conditions. Otherwise it could be rotating, right? So if you have something like this, and you push this way and you push that way, and this is the axis of rotation, it's not an equilibrium. Even though up equals down, it will rotate. You're gonna have a torque. To have a static equilibrium, you need those two conditions. Okay, so up is F2, down is F1 plus the weight. Okay, so we have F2, we already know, equals F1, that's what we want, plus 530. Okay? Do it. More you do, better it is, right? It's reviewing. So F1 will be, do it, subtract 946 Newton. Do you get that? But it's in magnitude, right? F1 is down. So if I want to write it as a vector, it will be negative F1. Do you agree? Yes? You are already in Thanksgiving? Okay, and I didn't, a different way to do it, okay? I could have decided to take my axis of rotation here. I can change. So a torque depends on the location on the axis of rotation. You can take it wherever it pleases you. So if I change it, okay, so now the torque applied by F2, it's going to be 0. So I can say the sum of the clockwise torque equals the sum of the counterclockwise torque. So that will be, so in that case, that's so relative to this one will want to go clockwise, and this one is going counterclockwise. So clockwise 530, and now I have to change the distance, right? So it's going to be 3.9 minus 1.4 equals F1 times 1.4. So you could have done that. Okay, so in a static equilibrium, you decide where is the fulcrum. The axis of rotation can be placed where it's the most convenient. So you do it to get rid of forces in the equation, right? So if you place it here, you are getting rid of F2. So if you do that, you're going to get the same thing. Okay? Any question? So static equilibrium, this is not a static equilibrium. Even though up equals down, there will be, it's called couple moment. You have a couple, right? So it's going to rotate. So it's not a static equilibrium. It's not in torque equilibrium. It's in the force equilibrium. The object is in force equilibrium, but not torque equilibrium. Yes. It will rotate. Because if you take a pen and I push here and I pull there, it will rotate. It's like the wheel, the steering wheel of a car. You push there and you push there, so it's gonna rotate. Okay, so this is a very classic problem. So before doing this one, because this one you have to buckle up. There is a very nice video. So this YouTube channel is called Veritasium, and it has to do with torque, equilibrium, force equilibrium, and gyroscope. So I don't know if you know this video. He made two videos, very good video. He has very nice, very videos. It's called Veritasium, from it means truth. So anyway, it's the anti-gravity wheel video. So this is an athlete, so a lot of muscles here, and this one is only 45 pounds. Only 45 pounds. 45 pounds you can easily lift, right? But this one, he was not able to lift it above his head. You see, because you see this, the weight is mostly in there. So the question is, how come he cannot lift 45 pounds when everyone can lift 45 pounds? It's not that hard. The reason is because it's in a force equilibrium, but not torque equilibrium. So to provide the counter torque, you need to provide a counter torque so it doesn't fall down, it doesn't rotate. You need to apply a huge force, right? You have to push this way, and here you have to pull up to make sure it's in equilibrium. So it takes a lot of strength. And he was not able to do it even though he is an athlete. And so you see, not only up has to be equals to down, but you have to push with one hand, pull with the other hand, so it doesn't rotate. And that takes a lot of effort. But there is a trick. So because here there is a torque. The torque comes from gravity. Gravity wants to make it fall, right? Because all the weight is here. But there is a trick. Turns out if you spin the wheel, if you make the spin wheel, if you make the wheel spinning, then the torque will not make it fall, it will make it process, right? Like a gyroscope, it will process. It will be so busy processing that you don't have to provide a counter torque. So, so this is the solution, but okay, he's gonna so I don't know if he's showing you. Oh, now I'm lost. So the scale doesn't matter. You can forget about the scale, but you see, this is spinning. The wheel is spinning, and then he can lift above his head.
Seems the apparatus doesn't get heavier or
Okay, I'm gonna skip.
Excellent. Great. 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 It was first performed by Blake Mark. Experiment. She's not wondering, right? But you don't like the child. He sure makes it look easy, doesn't he? Watching again carefully. Spinning wheel. So far, one was missed. Professor Lake.
So he can lift above his head. This is 40 pounds. The other one is 45 pounds. only because the wheel is spinning. If the wheel doesn't spin, even an athlete cannot lift above his head.
He claims the gyroscope's properties couldn't be fully explained by Newton's laws of motion. I disagree. In order to understand why a wheel feels so light, we first have to consider why it feels heavy when it's not spinning. Holding the shaft horizontally, you clearly need to provide an upward force equal to the downward weight of the wheel. But this is not enough, because with only these two forces, there would be a net torque causing the apparatus to rotate. So you need to create a counter torque in addition to supporting the weight of the wheel. This requires pushing down with one hand and pulling up with the other. And the upward force must be greater than the downward force by an amount equal to the weight of the wheel. So the force on each of your hands is significantly greater than the weight of the wheel. Now, once the wheel is spinning, the torque due to its weight now causes it to precess rather than fall to the ground. Therefore, no counter torque is necessary. You only need to supply an upward force equal to the wheel's weight, so it feels lighter. Now, the trick to lifting a wheel over your head is to push it forwards as you release it. Lengthweight knew this. If you force a gyroscope to precess faster, it lifts up. Higher precession and a process. The weight doesn't change. Similarly, if you slow the precession of a gyroscope, it goes down. Slide the precession and it falls dramatically. Roger, you right? Hard to go back to the way that that's all that precision. They cut side, it becomes a lot better. You see that too from having felt it. But it does.
You see, the wheel is spinning. If the wheel doesn't spin, you cannot lift above your head, even though it's 45 pounds, because you have to provide more than 45 pounds, because you have to provide a counter torque to counter gravity. But if it's spinning, gravity is doing something else. It makes the wheel process, right, going around, and it doesn't make it fall. So that's a gyroscope effect.
All I have to do is support the weight of the disc, but I don't need to provide any torque with my hand to counter that gravitational force. That's what makes it feel so awkward when you're trying to hold it when it's static.
So if you're interested, you want to watch the whole video, you will find it on YouTube. It's called Anti-Gravity Wheel, but not this one. This one is explained. Okay, it's super cool. So anyway, my point is that not only up equals down, right equals left, but you have counter clock torque equals clock torque. So now it's challenging problem, typical problem. So first of all, which one will be the free body diagram? So we have a ladder here on the wall, and here there is no friction on the wall. No friction on the wall, but you have friction on the floor. What do you think will be the correct free body diagram? Huh? B. So D? Yes, it's D. Okay, because you push on the wall push back on you. So that will be a normal force. Normal means perpendicular, so it's always perpendicular. Here it's also pushing on the floor is pushing back. It's like any surface is made of those little springs, push back, but it's not the same force, right? Here you can call it N1 and here you can call it N2, and that will be the static friction. And it's a whole thing in construction because you have to follow the rules. Because what's going to happen if you go up here at some point it might slide. So you have to follow the rule. Okay, many accidents can happen like this. You have to be very careful. So anyway, free body diagram will be D. So let's try to solve this problem. And first of all, I want to go back to the second definition of torque. Remember, I told you you have three definitions. It depends on the problem, the which one you want to use. One definition is using the lever arm. Okay, so one definition of torques. If you want to find torques, you have three ways. You can use the cross product. You can use R times the perpendicular component of the force, or that's what we're going to use. You can extend the force here. This is called the line of action, and you take the perpendicular distance. So that is called the perpendicular distance, and it's called also the lever arm. So sometimes it's easier to do that. So the force applied by F relative to your axis of rotation will be the magnitude of F times the lever arm. And to find the lever arm, then you know this angle or you know that angle, so you use trigonometry. So sometimes it's easier to use that definition. You can use the cross product or you can use the perpendicular. So we're going to use this one. Okay. So first of all, do your free body diagram again on your notebook. So you have to do it. So do the free body diagram. And we want to find how far can you climb before there is no more equilibrium. So it's a static equilibrium. We're going to write down all the equations that we can for equilibrium. So first, do your free body diagram. Okay. And this is given. So here you have some static friction, mu. So here you have static friction between the floor and the ladder. So what do we know? We have the normal force here. I'm going to call that N sub 1. Okay, so that will be to the left. Obviously, you need something to the right. So that will be the static friction. So you have static friction. If you have one pointing to the left, you need one pointing to the right. And then you have the mass. So we suppose the ladder here does not have any weight. So we have here mg. So that will be the mass of the guy. And we have the normal force here, N2. So you see N2 equals mg, up equals down, N1 equals the static friction. So that's easy. But now we want to express the torque equilibrium. So I'm going to put my axis of rotation here. Because if I do that, I get rid of this and I'm going to get rid of that. Okay? So I'm going to do the torque of N2 relative to the axis of rotation. It's going to be the torque of the static friction relative to the axis of rotation. That's going to be 0. Bye-bye. I'm done with you. Okay. Now, this one wants to do what is that? Counterclockwise. Yes. And this one wants to do clockwise. Agree? Okay. So now we're going to have the torque from N2, N1, sorry, relative to the axis of rotation will be equal to the torque applied by the weight relative to the axis of rotation. That's easy. So now try to use the lever arm to find the expression of the torque. So N1, the first thing you do, you're gonna extend the line of action. Okay, so you extend the force. You start from the axis of rotation and you find the perpendicular distance. So that distance here. Agree? We want to find this distance here, right? You can call that, I don't know, R1 perpendicular. So we want to find this distance here. And that angle here is theta. Okay, so that will be sine. Do you agree? Okay, because we have the angle here, theta. So that side is the opposite side. And this is L. So we're going to have N1 times L sine theta. This is called the lever arm. Okay, you can do the other definition, but it's a little bit harder with, you're not sure cosine, sine. This one will be easier. And then you have the torque applied by mg. So same thing, you extend the line of action. So I'm extending the line of action here, and you do the perpendicular distance. You see, this is your angle theta. That will be your perpendicular distance. Are you with me? So in that case, it will be a cosine. So it's going to be mg. This distance here is r. So r cosine. And you say, okay, we are good here because you see a sine, you see a cosine. Somewhere you know that you're going to have a tangent popping up. Agree so far? Okay, so lever arm. Any question? R is here. R is the distance between the axis of rotation and where the weight is applied, because you have the person on the ladder. Right? So you extend the line of action. You start from the axis of rotation and you project. You take the perpendicular distance. So that distance relative to this angle is the cosine. Question? Okay, and then it's easy because we're going to say, okay, left equals right. Left equals right. So N1 is going to be right is the static friction. Yes? But the static friction is maximum. Okay, that will be the maximum you can get. If it's smaller than that, you're fine. It's not going to be sliding. But as you move up, you are pushing, you are putting more stress on the floor, right? You are pushing more on the floor. So the static friction will increase until it's going to reach a maximum. If you go over that, it's going to slide. You can do the experiment, right? You take a ladder and see up to where you can go. Not my responsibility. And see, actually, you don't need to do that. You take a ladder for a demo and you take some weight. And you see, you hook the weight here, nothing happen. You hook the weight here, nothing happen. You hook the weight here, like 5 pounds, nothing happen. But you will reach a level where it's gonna start sliding because you have reached the maximum static friction. And the maximum static friction is the coefficient, only the maximum, right? Times n2. Agree? Right? Because that by definition, the maximum is the coefficient times the normal force. And we are here. Agree? Do you agree? You say, yes, we agree. Okay, good. And then you have up equals down. So up is N2 equals down mg. So we have 3 equations. And we want just a relationship between r, theta, and L. So I'm going to plug N1 into here. I'm going to plug N2 into there. Agree? Okay, do it. So it's easier if you do it. Plug N1 in equation 1. Plug N2 Yeah, plug N2 as well. So I'm going to plug N1. So this is equation 2, this is equation 3, and this is equation 1. So I'm going to plug equation 2 into equation 1. So I'm going to have mu s N2 L sine theta equals mg r cosine theta. Agree? Okay, I'm going to call that equation 4. Now I'm going to plug equation 3 into equation 4. So I'm going to have mu s n2 L sine theta equals, so mg is n2, so n2 r cosine theta. Okay, so now you can do it. You can cross out n2 both sides and try to get to isolate r. That's the question is r. How far can you climb until it starts to slide? When it starts to slide, that means you have reached the maximum static friction. If you're an engineer, you should try that. You have a small ladder and you put 5 pounds here, 5 pounds there, 5 pounds here, until it's gonna slide. Of course, it depends on the angle here. Larger angle, more dangerous. Don't climb yourself. Okay. So R equals mu s, so static friction times L and tan. You're right. So interestingly, it doesn't depend on the mass. So here you have a relationship to know exactly, given the static friction that you get, given the angle, how far can you go without slipping, without, dead. Okay, so I'm sure I forgot, but I'm sure in your textbook they have one problem like this. So you should see how they do it. Okay. So if you want to go, maybe you are not you don't want to go here. Maybe you want to go all the way up. Maybe you want to be able to go all the way up and then you can climb on the roof, right? So if you want to go all the way up, you want to make sure that R will be larger than L. Agree? Right? So in that case, you want to have this larger than L. So you want to have this larger than 1. Agree? Because you want to be able to go all the way up. Just not stop here. You want to go all the way up. So you want the distance where you stop to be larger than the length of your ladder. Okay, so in that case, you want to go all the way up. So let's say we have a coefficient equals to 0.26. So the tan has to be larger than 1 over 0.26, right? So it's like an engineering problem. So you take your calculator and you do arc tangent, tan to the minus 1, 0.26. So the angle should be larger than 75, yes, 75 degrees. Okay, so you want to be able you have to be careful. You want a larger angle, meaning you want the ladder here to be closer to the wall. You can do that with your guts. You can feel that closer the ladder is from the wall, harder it will be to reach the maximum static friction. You survive? If you survive, that's good. So the OSHA says that the distance from the ladder base to wall should be 1/4 of the ladder length. So it's about a rule of thumb, right? I mean, closer is better, and you want someone to hold it. Okay. So where is the center of gravity, you think, here? See, right? It makes sense, right? So you have the weight down, and you can do the same type of computation. Okay, so you can do that on your own. Okay, so let's do the beam. Any question? Okay, so do the beam. Typical question for civil engineering. It's a static equilibrium. And we have one beam for the final. It's a typical question. Now you have the mass of the beam and the mass of the guy. And the system is the beam. Remember, we have to put something in the bag. Inside the bag, you have the beam. So you are looking at the force applied to the beam. And so first of all, they want the tension. They want the tension. Let's find the tension using torques. First, we want to find the tension using torques, and then we'll move to whatever. You criticize the beam. Okay, so 600 Newton, which is 60 to 120 pounds, which is very lightweight. And this is 40 pounds. 120 pounds seems very, very, very small. Okay, so do your free body diagram. Imagine this is inside your bag, and you have to draw all the forces acting on it. Okay, so do your free body diagram. Do it, do it, do it, do it. So you have the tension. And then you have the weight of the beam. Which is at the center of gravity. And then you have the guy. And that's when it depends how you want to do it. You see, you have a bolt here. So you can think of it as push into the wall is going to push back. So here you have a normal force, and it wants to slide, but no, it can't. So you have a force pushing in this direction. I'm going to call that the static friction. It's not really static friction because it's secure, but I'm going to call it this way. Now you're in civil engineering, they don't do it this way. They will say, okay, we're going to call that a reaction force. So they will make that vector here R. So then you can call that the X component and you can call it the Y component. Agree? So then you take, because you want the tension, you want to get rid of those guys here. So you want to put the axis of rotation right there. Even if nothing rotates, you can take it wherever you want. So if you take it here, this one wants to make it turn, push this way. So that will be counterclockwise. This one will be clockwise, and this one will be clockwise. Agree? For the torque here, you have two ways. You can do the lever arm or you can do the perpendicular component. It's up to you. Because there is an equilibrium, the sum of the clockwise torque will be equals to the sum of the counterclockwise torque relative to the axis of rotation. So try to do it, give you some time. So for the torque here, you have two ways, right? You can say, okay, it has a y component here and it has a x component. So the torque will be provided by the y component. So you can find the y component. Or you can extend the line of action and find the lever arm. So you have two ways to do it. Okay, you can do so clockwise. Clockwise. I have a clockwise here and I have a clockwise there. Clockwise everywhere. So you have 200 times. So that will be the typical mistake, is to forget to multiply by the distance between where the force is applied and the axis of rotation. So that will be 4. Okay, because it's at the center. Plus 600 times 2. You're right. That should be equals 2. So again, you have different way to do it. I can say it's going to be the y component of t times the distance. So that will be a sine. You see, that's a parallelogram. So I can say 200 times 4 plus 600 times 2 equals t sine 53 times 8. Okay. So you see it's a parallelogram here. Remember, you go from the tail to the head. Oh, yes, from the tail to the head, y component, x component. So this component is busy pushing into the wall. It's push into the wall is going to push back. This component here is busy balancing out the weight. So if you do it, you should get, do you get? Yes, thank you. 313 Newton. Agree? Yes.
You got the answer using forces. Everything up was that.
We're going to do it. We're going to do it. If we do it, like right now, you will have 1, 2, 3 unknown and one equation. Oh, no, 3 unknown and 2 equation because you have everything to the right equals everything to the left. But now we're going to do it. Okay, because we have one answer, but they want the static friction and the normal force. You cannot use only up equals down and right equals left because you don't have enough equation for the number of unknown. So if I do everything right equals everything left, pushing to the right you have the normal force, pushing to the left you have the x component. X component is a cosine. Agree? Yes? So the normal force will be yes, yes. Yes. What's your name again? Roberto. Yes. Normal force. 188 Newton. Do you all agree? Okay. So I did up equals down. And now I'm gonna erase this. Yes. So I'm gonna do everything up equals everything down. So up, you're gonna have the y component plus the static friction. I call it the static friction, but your engineer professor will call it Ry. Equals down, which is 200 plus 600. Okay, so the static friction will be 800 minus T. So it was 313 sine 53. So what do you get? 550 exactly. Thank you. 550. And now they want to find that component here because in engineering they will say, okay, that's a x component, that's a y component. So all you have to do is to use Pythagorean theorem, right? So 188 square plus 550 square. Yes, 581 Newton. And you can even find it's a vector. We are finding a vector. So we found the magnitude and we can find that angle here, right? Which is the arc tangent opposite. What is opposite is 550 over 188. So then we'll have defined a vector completely. So that's a question, like a typical problem in civil engineering.
So we'd have to do every single step. All that was to get the tension.
So the tension we did it for the torque. So if you want to skip that, you have to say right equals left, and so you need the tension. What you could have done is to move the axis of rotation. You could have moved it here, for example, and then move it there, and you can do it without up equals down and left equals right. What's your name again? Michael Roberto. Right. If you have any question, let me know. So you see here, it comes from a book for engineers, and you see they don't show normal force or static force. They just show this vector here, and they call that a reaction force. Reaction from the wall, because the wall is being bullied, so he has to fight back. So they call that a reaction force. See? That vector here is called a reaction force. And they're going to find that angle here, the magnitude there. So that's how they do it. You can do it this way too, right? So it's a good way to do it. It decompose the vectors into their components. So then you get over with that. Okay, and that's how you can solve it as well. Okay, static friction it's very useful because there is this demo which is very famous, right? So you have the torque from the weight. So this is pulling down, so there is a torque this way. But as you keep wrapping and wrapping and wrapping, it's like a compounding effect. You keep building up, building up, building up the static friction. Enough for that to be in equilibrium. And then there is a very advanced computations to do all the math. Maybe your book will do it. So here it's not in equilibrium, obviously. So you can do that as a demo. So you have points not in equilibrium. It's very famous for people sailing. Right? Not in equilibrium. I don't know, it's stuck. Oh. Another one. I don't know why it stopped like this. Keep going. I don't know if it's my computer or... Okay, it's frozen. Everything is frozen. Well, you get the idea. Oh, I'm frozen. It's okay. Okay, and if you Google it, it's called belt and wrap friction, and you have a whole computation. Let's see. Oh, excuse me. Okay, you can do that on your own. And the computation is very interesting if you want to go to civil engineering. Okay, uh, there is just this definition. Moment of a couple is when you have two force applied, like a steering wheel, and the magnitude is the same, and they are parallel to each other. So when you do the computation, the net torque will be equals to just the magnitude times the distance between them. Just a parenthesis. We equilibrium. So you have different types of equilibrium. So this is a stable equilibrium. This is an unstable equilibrium. So to get an equilibrium, you need to have the potential energy to be zero, right? It has to be as small as possible, but you need to have this curve here, right? So that will be stable, that will be unstable. Center of mass. Center of mass is very interesting because um, all objects will behave as their mass is at the center of mass, is at the center of gravity. And the center of mass will respond only to external forces, right? So it's here I found it cool. I took the picture because you see the center of mass is here. To have a stable equilibrium, you want to make sure that your center of mass is above the connection here between you and the base. So it has to be in line with the base of the object. Okay, center of mass can be outside the object. See, center of mass. So center of mass has to be exactly above your contact area. So my computer is not great. Hmm. Where is it? So just for Parenthesis here, men and women is not the same. Center of mass for men is higher, for women is lower, obviously, because of the pelvic floor here. So that means that women can do things that men can't. If you go to physical therapy, you will learn about that. I don't know if I have a short video to show you. So if you are taking biomechanics, you have a lot of interesting examples. So for example, here you see you can take this axis of rotation is over there. The body weight will pull down. So that will be a torque, clockwise torque. And then here you will have a muscles. Okay, so the muscle will be, so this one pull down and that muscle pull in the opposite torque, right? So you have an equilibrium. And here, okay, just show you very quick demos that you can do if you want. Okay, I cannot find anything. Oh, that's me trying to find a center of mass. Hi guys. I cannot stand my voice. So let's say you have a shape, okay? So what you will do, you take a string with a weight, okay? So you have your string here and you have the weight pulling down. So you know that you trace the line and the center of mass will be somewhere along that line. So you do that. But we don't know where. So then you take your shape and you're gonna move like this, right? And you do the same thing. Okay, that's a demo you can take, right? You take a cardboard, you cut it down with a weird shape. You take a string with a weight, right? You're hanging it there. And you know the center of mass will be somewhere along that line, okay? Because at the center of mass, the weight is pulling down. So now we know we have two lines. We know the center of mass should be somewhere there. And you can do even a third line. Do a third line here. And now you can put your finger just there, and that's going to be an equilibrium. So all the torques applied about this axis of rotation will be equals to 0. So that will be the definition. How do we find the center of mass? Okay. Just for the fun. And then we go back to be serious.
You're up to video yourself doing these challenges and post them on social media. Such as Facebook, Twitter, or Instagram. Make sure you use the hashtag Sorry on the Fly. Are you ready? Let's do this. Challenges are all about gravity and finding your center of mass. The term gravity is used to describe a force of gravitation on an object or near the surface of a celestial body, such as Earth, the Moon, or some other planet. Now, this force pulls on all mass. All mass exerts gravitational force, from the smallest subatomic particle to the largest star in the universe. The greater the mass, the greater the gravitational force. Now, the center of mass is a point in an object where the mass or the weight seems to be concentrated. This point can be a physical object or it can be a reality object as well. In a round object, equally distributed mass, the center of the sphere is the center of mass. To find the center of the mass within a ring, it's going to take a little bit more work. And in this case, a lot more fun. First challenge is the belt press. Here's how you do it. First, place a chair against the wall so that it cannot slide back. Sit in the chair with your feet flat on the floor in front of the chair. Your feet must not be slanted or aimed side. Have a partner gently place their thumb on your forehead. Now, try to stand up. Backwards. So hard to chair and not over your feet. The next challenge is the chair lift. Here's how you do this one. Place a chair along the wall and stand so that your feet are not under the chair. Bend over at the waist and place your head on the wall so that your back is flat and parallel to the ground. Now lift the chair and try to stand up.
How come they cannot do it? Right, exactly. Because men, the center of mass is higher and women is lower. Right.
Challenge is the quarter graph. Here's how you do this. Start this one by standing with your feet against the wall. Now place a quarter on the floor at the tips of your feet. Your back, the back of your feet against the wall. Bend over and try to pick up the quarter. That one's a little bit difficult. When people bend over, their rear ends extend to balance, which keeps their center of mass over their feet. Against the wall, an individual's rear end cannot counterbalance. Now, my final challenge to you is the leg raise. Here's how you do this one. Simply stand sideways against the wall, with one shoulder against the wall, with the same side leg against the wall as well. Now, simply try to raise the opposite leg without holding on any left.
Okay. And likewise, the Tower of Pisa, it's lean, but it doesn't fall because the center of mass is just above the contact between the tower and the ground. Otherwise, it will topple. So a lot of applications here. Okay, so here, super cool. If you can do that, I will give you extra credit. The center of mass, it's not in the pelvic here, it's just there, just above his uh, hands here, okay, this area. So then you can have an equilibrium. And there is yoga. In yoga, it's very big. There is a pose where, yeah, try. It's very challenging, okay, because you have to lift your but you have to explain the physics, right? I don't know what is that. Oh, we already did this one. That there is a yoga pose where you can lift yourself with your hand. I don't know if you know this one. It's like a frog or a toad. The frog, right? It has to be also with the center of mass. It's not that easy. Everything yoga or strength training, you have to be aware of your center of mass, right? If you do Bulgarian squat, for example, you want to make sure that the center of mass is above the foot that's touching the ground. Not easy, right? That's the one we saw. Okay, very big also in equilibrium. So you want the center, so you have the center of buoyancy and you have the center of gravity. So that will be at when you are displacing water, something is submerged, right? The the weight of the liquid displaced will be equals to the buoyant force pushing up. But you want the center of gravity to be below that center here. So this is the center of the water displaced that has been displaced. If it is this way, you see what's going to happen? It will apply a torque and it will go back to this and it's fine. However, if you do the mistake, and it has been done, if you put too much weight on the top here and the center of buoyancy didn't move, then you have a torque, but the torque, it will be make it go down, right? It will make it worse, unstable. Okay, center of mass is also in astronomy. You have binary systems. So you have a star and a planet, or you have two stars. They're going to orbit, but they orbit their center of mass, their common center of mass. So even when you have the Earth and the Moon, right, to explain the tides, you have to understand that they both orbit their center of mass, even though the center of mass is inside the Earth, and that will be the Moon, for example. But the Earth wobble, so it has a centrifugal force applied to the ocean. So it's like there is the centrifugal force and there is gravity. Okay, so that's how we can explain the tide. So anyway, if you have Jupiter here and the Sun, the center of mass will be inside the Sun, but the Sun will wobble every 12 years because it takes Jupiter 12 years, right? If the masses are the same, so then you have your center of mass. How do we find the center of mass? The equation that we use also for binary systems to find the masses of stars will be M1R1 equals M2R2. So, or M1R1 equals M2R2. And you find the center of mass. You use also which leads you to conservation of momentum, right? So this one pulls on one, so one pulls on two. So M1V1 equals M2V2. And then you have Kepler third law. So anyway, it's like a seesaw. So you have to be careful with the center of mass. So that happened to it happened to airplanes sometimes. You see, there was a torque here about the axis of rotation. It does something like this. Okay, this is not possible. I have to blank here. But you can imagine what is under the blue square. He cheated here, right? He had some hooks. There was hooks under his shoes. Otherwise, it can be. So you have the torque from gravity, but you have a counter torque here from friction, right? They had like some hooks under the shoes. This is a super cool song. So anyway, one thing that you have to understand is that the center of mass only responds to external forces. So if you throw something in the air, right, and you make a very complex motion, so not only it's moving forward, but it's rotating at the same time, the center of mass says, I don't care what you are doing. I'm only responding to gravity because this is the external force. So the center of mass doesn't care that you have rotation about the center of mass. The center of mass will follow a projectile motion. Okay, so it means the acceleration of the center of mass, okay, will respond only to external forces, which is in that case the weight, and you will have a projectile motion. It says MIT. I don't know if I have the video for MIT. But you get the idea. So this was a big breakthrough, but I forgot his name. So the center of mass responds only to gravity. So that there is so much height that you can go. You cannot go higher because it's dictated by gravity and it's a projectile motion. And this guy had for the first time the idea to flip, right, to do it on the back. And even though the center of gravity could not go higher, but his body did, and that's what counted. He's very famous. I'm sure I have his name somewhere. Boom. You don't know his name? He's the one who changed everything. Uh, no. Ah, I don't know if his name is Rick something. This guy. Okay, so he's the one who came with the idea for the first time to jump, but on the back, because again the center of mass cannot go higher. It's impossible, but the body can. So the center of mass obeys external forces, but you can manipulate it with your body. Okay, so you can arrange your body around the center of mass, and that's what he did. So of course he won the world record. So it was a big breakthrough. So likewise here, when she jumps, it seems that she's hovering. She's not really hovering, she's just changing the distribution of mass around the center of mass. But the center of mass is still following a projectile motion. Now in 3D, it can get very complicated, but you see the center of mass will just go, in that case here, it will firework, it will go up and down. It's all what we want to do, up and down. So when there is an explosion, all those pieces here, they have to go in such a way that the center of mass will still go up and down. Okay, so the center of mass always obey gravity in that case. It will go up and down or projectile motion. So all the masses here has have to rearrange themselves to keep the center of mass at the same position following free fall. So that's why they all go in different directions. Okay, same thing. So you have very cool problems with those kind of questions. You see, it will the center of mass. So there is an explosion here. So the center of mass will keep going along a projectile because it only obeys to external forces, which is just gravity. So those two pieces here have to make sure to rearrange themselves in such a way that the center of mass will be here. Same thing here with there is a missiles exploding. Those pieces will arrange themselves, distribute themselves, such as the center of mass will keep going along a projectile motion. So it's a lot of things in application in the explosion, missiles, and things like this, and very cool problems, right, that you can do. Okay, same thing here. You move forward, the boat is going to move backward because in that case, it's an isolated system. So there is no external forces. No external forces means that the center of mass has to stay at the same location because it's not acted upon by an unbalanced force. So those two, you and the boat, okay, you can move, they will it will be rearrange themselves, the masses will arrange themselves such as the center of mass will stay same place. So if you move forward, the boat will move back to make sure the center of mass will stay at the same place. Isn't that interesting? And then we can use an equation to find the location of the center of mass. And again, it's based on static equilibrium. So M1 R1 equals M2 R2. Then you define your x-axis, you massage, you shake a little bit, and you have the equation here. So that equation is the location of the center of mass. You see, it looks like a weighted average. See, M1 over the total mass, M2 over the total mass. It's like a weighted average, right? And you can do the math and blah blah, and then it can become a headache. So if you want to go to engineer, I highly recommend that you try on your own those problems here. So see here, it's not that hard. You are looking at trying to find a center of mass. So you have one equation for x, one equation for y. This one is a little bit more challenging, okay, because you have to do density. Okay, you have to work with density. So you can do that on your own, and can be also very challenging here. Some calculus, it doesn't hurt. You can do that on your own, and blah blah and blah blah. Okay, we're done.